Hey guys, continuation of chapter 5, probability. This section is section 2, the addition rule and complements. Let's see, so two events are disjoint if they have no outcome in common. Another name for disjoint events is mutually exclusive events. So we often draw pictures of events using Venn diagrams. These pictures represent events as circles enclosed in a rectangle. Rectangle represents the sample space and each circle represents an event. For example, suppose we randomly select a chip from a bag. For each chip, the bag is labeled from 0 to 9. Let E represent the event, choose a number less than or equal to 2. And let F represent the event, choose a number greater than or equal to 8. So less than or equal to 2 from these numbers up here, what we would have would be 0, 1, and 2, because 0 is less than 2, 1 is less than 2, 2 is equal to 2, so that will satisfy choose a number less than or equal to 2. And now for the opposite, choose a number greater than or equal to 8. So here we would start off with 8 and go to all the numbers higher than that. So 8 and 9 happen to be these over here. These two are disjoint because there is not one number that falls into both of these categories. So that's what makes them disjoint. With this, looking at the probability, so remember we said the probability of E were numbers less than or equal to 2. So out of all the 10 numbers, here we have 3 out of 10 that are less than or equal to 2. So here we would have just that. And for F greater than or equal to 8 would be these numbers here. So 2, just 2 numbers out of the entire 10. Remember the sample size was 10 different numbers. This would be 2 out of 10. And all they did here was divide the 2 numbers. Looking at the sum of those two, picking either a number less than or equal to 2 or a number greater than or equal to 3 or greater than or equal to 8. We have 1, 2, 3, 4, 5 out of all the 10 that we had all together. So that would be 5 divided by 10 gives us 0.5. Another way we could see it is individually looking at these, looking at the probability of event E happening and the probability of event F happening and adding those two together. It would give us the exact same thing. So remember, probability of E was 0.3. Probability of F was 0.2. So adding those two together, 0.5. And now for our addition rule. So if E and F are disjoint or mutually exclusive events, then the probability of E or F is equal to the probability of E plus the probability of F. So this only happens with disjoint events. So remember, disjoint, there is not one thing that the two events have in common, so therefore we're able to do all of this. All right, so the addition rule for disjoint events can be extended to more than just 2 events. So in general, if event E, F, G each have no outcomes in common, they are pairwise disjoint. So basically what we're saying is out of our population or our sample space, if we have 1, 2, 3 events, or even 4 events or 5 disjoint events where not one value overlaps another. So there's not one value that belongs to 2 different events. So if we have a bunch of different disjoint events, we're able to add those together. Let's clear this up. So looking at this over here, introducing some a number less than or equal to like 5 less than or equal to a number less than or equal to 6 would give us this value right here. So looking at those, probability of E is 3 out of 10, probability of F 2 out of 10, and this new probability of G is 2 out of 10. So looking at those, adding those up, we have 0.3, 0.2 plus 0.2, that gives us 0.7, but let's see what it ends up being altogether. We have 1, 2, 3, 4, 5, 6, 7. So 7 out of those 10, we could plug it into a calculator and it does give us 0.7, which is the exact same thing, which is what we needed here. Here we go. Our number system consists of 0 through 9. So digits 0, 1, 2, 3, 4, 5, all the way up to 9. So because we do not write numbers such as 12 as 0, 1, 2, the first digit is the first significant digit in any number must be 1, 2, 3, 4, 5, all the way up to 9. So we may think at each digit that each digit appears with equal frequencies so that each digit has a probability of 1 out of 9 of being the first significant digit, but this isn't true. So looking at this here, we have our digits 1 through 9, all of these right here, and we have their probabilities of appearing in a number. So this could be any number. It could be a phone number, it could be a serial number. So this is all of that data kind of wrapped into one. So from here, the question is verify that Benford's law is a probability model. So remember, Benford's are not Benford's. A probability model will consist of two different conditions. Let's take a snapshot of this really quick so we could take it to Excel. And over here. Okay, so over here, insert data from table, picture from file. And here we go. So table 5, probabilities, looks good, insert. And now we have this data. So remember the two conditions that we need to satisfy in order for this to be a probability model. The first, all the probabilities have to be between 0 and 1. So what we'll do is find numbers that are less than 0 and numbers that are greater than 1. So numbers that are less than 0 are going to be negative numbers. And it looks like all of these here are positive numbers. Perfect. Numbers greater than 1, since all of these have decimals, there should be a whole number in front of that decimal. So 0.0. So these all start with 0. There's not one that is greater than 1. So for that, we pass this condition. And part 2, we have, let's see, the sum of all the probabilities is equal to 1. So the way we could find this is to find simply the sum of all of these. So sum of the probabilities of E. And I was hoping it didn't do that. So equals sum of these. And the sum is equal to 1. So because both of these two are satisfied, then we could say that this is a probability model. All right, each probability 0, 1, sum of all of them is 1. All right, so part B, use Benford's law to determine the probability that a randomly selected first digit is 1 or 2. So verbally, we're looking at the probability of 1 or 2. And let's write it down. All right, probability of 1 or 2. So since these are disjoint events, we don't like one is not part of both 1 and 2, 2 is not part of both 1 and 2. So these are two disjoint events, so we could use our addition rule. So here we have probability of 1 plus the probability of 2. That's going to give us a probability of both of them. So we have that coming over here. Let's write it a little bit lower. So probability of 1 plus probability of 2. So here we see that the probability of 1 is 0.301. And the probability of 2 is 0.176. So now adding those two together, have Excel do it for us. So equal to this value plus this value, 0.477. And there we go. That's our probability. So the probability that both of them are selected or randomly selecting both of them ends up being 0.477. Clear this. Okay, so if we look at 100 numbers, we would expect about 48 of them to begin with 1 or 2. Part C, use Benford's law to determine the probability that a randomly selected first digit is at least 6. So probability of at least 6. So the way that we're going to look at this is with the numbers. So let's write all of them out. So not 10, so just up to 9. All right, so using this, use Benford's law to determine the probability that a randomly selected digit, first digit is at least 6. So we know that 0 is not going to be one of them because 0 is not a significant digit. But now we look at the words at least 6. So 1 is not at least 6. 9 is at least 6. It's greater than 6. So since 1 does not fall into the category, let's get to numbers that we should recognize. All right, so let's take a look at 5. Does 5 represent a number that's at least 6? No. So at least 6 represents these right here. So let's go back to this. So this is equal to the probability of x. So our variable x being greater than or equal to 6. So in other words, this is a probability of 6 or 7 or 8 or 9. And from here, since these are all independent events, we're able to separate them and go from there as a probability of 6 plus probability of 7 plus probability of 8 plus probability of 9. And let's bring it over here. So to where we could see all of the probabilities. And this is equal to probability of 6 is 0.0067 plus the probability of 7, 0.058. Probability of 8, 0.051 plus the probability of 9, 0.046. And now since these 4 are the ones that we want, are the ones that satisfy that condition, let's add those 4 together and it should give us this value right here. So equal to the sum of these values right here, 0.222. And bring it back over here. So this is our value. The probability of selecting or having a number or randomly selecting say 100 numbers, we would have about 22 of them be at least 6. And let's see if we missed anything. Nope. So at least 6 represents 6 or 7 or 8 or 9. The sum of all of those ended up being 0.22. If we look at 100 numbers, we would expect about 22 of them to begin with 6, 7, and 8. All right, so now suppose a single card is selected from a standard deck of cards, such that that one shown in such as one of these right here. So just to give you a quick little recap, if you guys don't know anything about cards, 52 standard deck of cards has 4 different suits. So we have the suit of spades, hearts, clubs, and diamonds. And each of them, each suit has 13 different cards. So one is replaced with an A or ace. Then we have 2 through 10. Then we have a jack, queen, and then a king. So that makes up the 13 different cards within each suit, and the 4 suits, 4 times 13 gives us that 52. All right, so now compute the probability of the event E drawing a king. So let's look at that in total. So we have probability of drawing a king. So that's equal to the probability, or not the probability, the number of ways of selecting a king divided by the number of the sample space. So we just talked about the sample space. So in total, there's 52 cards. And coming back here, there we go. So coming back here, we see that 1, 2, 3, 4, 5. All right, looking for the kings right here. So we have 1, 2, 3, 4 kings. They didn't say kings or queens, it's just kings. So there's 4 of those. So now 4 out of 52. Let's take this to Excel, see if we could computate it for us. So 4 divided by 52. Nope, equal to 4 divided by 4 divided by 52. And that one's already stuck as a date. So 0.077. And there we go. So one other way that we might see it is them just simplifying this equation. So we know that both top and bottom are divisible by 4. And that would give us 1 out of 52 divided by 4 is 13. So it would give us a 1 out of 13 or 0.077. And let's see what they give us. So 1 out of 13. Or we could be a little nitpicky and say about 0.077. All right, B, compute the probability of event E drawing a king or event F drawing a queen or event G drawing a jack. So looking at probability of E or F or G. So this is a probability of drawing a king or drawing a queen or drawing a jack. So there is not one card that could fall into either or like 2 categories at once. So they're all disjoint. So remember king, queen, and then jacks. So there is not one card that falls into jack and queen or jack and king or anything like that. So we're able to see these as independent events. So probability of king plus the probability of queen plus the probability of jack. So we just computed probability of king. That was 4 out of 52. Queen, there's 4 queens because there's 1 queen for each suit. So that's 4 out of 52. And same thing with jacks. there are 4 jacks in each suit out of the 52. Now, some fun math skills here. When we're adding fractions together, as long as the denominator is the same, we could add across the top. So here, 4 plus 4 plus 4 gives us 12 out of 52. And from here, we could simplify this by dividing both top and bottom by 4. So 12 divided by 4 is 3. 52 divided by 4 is 13. So 3 out of 13, or we could actually type it in here. So equal to 3 divided by 13. That gives us 0.23076, so 0.8. And that would be our probability. Let's see what we got. So standard deck of cards, 4 kings, 4 queens, 4 jacks, even E, F, and G are mutually exclusive. Addition rule, cool, 3 out of 13, or we could say that it was approximately 0.2308. All right, so now the general addition rule. So this is our general addition rule in the case that we have things that overlap. So notice that when we look at these regions, so event E is calling for, it looks like even numbers, I'm sorry, odd numbers, so 1, 3, 5, 7, and 9, versus F looks like it's numbers less than or equal to 4. So 0, 1, 2, 3, and 4. So 1 and 3 are being counted twice. So what we would do is subtract those. So subtract 1 and 3 because it's being counted twice. All right, so what they're showing here is, so computing by N or the number of E or F, we have 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. That's where they got that 8 from. If we were to have followed the original rule and looking at these numbers, so all the odd numbers, so 1, 2, 3, 4, 5. 5 plus probability of F being less than or equal to 4. We have 5 of those. We would have the entirety of the sample space, but notice that there are 2 digits out here that should not be there. And adding all of these together, we would end up with 8 over 10 or 4 over 2. So this is the actual probability. So what we're doing is subtracting the probability of E and F. So this is our generalized rule. So this would happen even with dependent or independent events or disjoint events, where we have probability of E plus probability of F minus a probability of E and F. So this part here would just be 0 for disjoint events. All right, so now looking at this, suppose a single card is selected from a standard 52 deck of cards. Compute the probability of event E, drawing a king or drawing a diamond. So we're looking at probability of king or diamond. Just using K for king right now. So probability of king or diamond. So now let's take a look at, or do they have a center deck of cards in the next one? No. Let's go back to our picture of the cards. So probability of king, we have these over here. Those are all kings. And we have our probability of diamond. Diamond is these here at the bottom. So I'm shading those in blue. So notice that over here, we have one card that falls into both categories. So both king and queen. So because of that, we're counting it twice, and we shouldn't be counting it twice. So let's take this over to our page. So we have 4 kings, 13 diamonds, and 1 that overlaps. All right, again, so probability of king or diamond. I'll just draw it out a diamond. All right, so probability of king or diamond. So this is a probability of king plus the probability of diamond. But notice that the king of diamonds is being counted twice, so we have to subtract at least one of them. So probability of king and diamond. Probability of king, there's 4 kings out of the entire 52 deck. Plus probability of diamonds, there's 13 cards per suit, so 13 over 52. And we're subtracting probability of king and diamond because it was counted twice, both in the king's probability and on the diamond's probability. So there's only one card out of the entire 52 that's both a king and a diamond. So now remember, when we're adding fractions, if the denominators are the same, we could just add or subtract across the top. So 4 plus 13 is 17, minus 1 is 16. So we have 16 over 52. Both top and bottom are divisible by 4. So we end up with 16 divided by 4 is 4. 52 divided by 4 is 13. So 4 out of 13, or equal to 4 divided by 13, 0.308. And there we go. Let's clear this out and see what they ended up getting. So again, probability of king plus probability of diamond minus probability of king and diamond. And again, here all they showed was the reduced fraction. So here is a contingency table where we have data kind of surrounding here. So we have males versus females. We have never married, married, widowed, divorced, or separated. And it looks like this is all in millions. So table 6 is called a contingency table or a two-way table because it relates two categories of data. The row variable is a marital status because each row in the table describes the marital status of the individual, and the column variable is the gender. Each box inside the table is called a cell. All right, so using the data in table 6, on the previous slide, we're going to answer these questions here. But now let's take a snapshot of the data so that way we could just put it on Excel, make it a little bit easier for us. And bring it to a new sheet. Insert data from picture. Looks like it captured a bunch of random stuff. Oh, the bar that you guys don't see. All right, so never married and females here. Let's get a better picture. Better. All right, much better. Okay, so here table 6 represents males in millions, females in millions, and then the marital status. So from here, the questions that they wanted to ask were A, determine the probability that a randomly selected US resident 15 or older is male. So let's see this. So what we could do is look at this and say total. And here, this would be equal to the sum of these. And same thing here. So the sum of the females versus the sum of the males, and same thing here. So equal to sum of these two. And there we go. Okay, so the total of never married, whether it be male or female, is 86.1. The sum of divorced male and female is 28. So we could see the sum of those two, and yep, there we go. And in total, the total of all of these and added with the total of all of these. So notice that it's still the same numbers, so equal to this plus this, 260.1. Both of these are the same numbers because they came from the same data. Kind of all works itself out. All right, so one more time. So 15 years older is male. So probability of male. So just think of it without looking at this table. So probability of male is N, the number of males divided by the number of the sample space. So here the number of males, all the males are going to be 126.9, and we're dividing it by the number of the sample space, 260.1. So remember, this is the total of the sum of all of these, which is the sum of all of this right here, and the sum of these two, which is again the sum of all of these two. So now dividing those two, we end up with, so equal to this number divided by this number. And that gives us 0.4879. So 0.4879. And we could actually look at that. So we would say probability of male is equal to male divided by the total. Yep, there we go. So there's that. The next one, determine the probability that a randomly selected US resident 15 years old or older is widowed. So now we're looking at probability of widowed. So now probability of widowed, we're looking at all of the widowed people. So widowed right here. So widowed divided by the total. And that's 0.0584. Next, determine the probability that a randomly selected resident 15 years or older is widowed or divorced. So widowed or divorced, according to this table, you could be, these are disjoint events. So probability of widowed or divorced. There we go. Widowed or divorced. So it looks like these two are disjoint events. We could add and subtract them together. So probability of widowed or divorced would be equal to the probability of widowed plus the probability of divorced. So let's kind of look at those instead. So widowed or divorced. We have probability of widowed. Let's look at probability of divorce. So that's equal to divorce, all the divorce divided by the total. There we go. So now this is equal to the probability of widowed plus the probability of divorced. And that's it there. And lastly, determine the probability that a randomly selected resident 15 years or older is male or widowed. So male, probability of male or widowed. All right, so now looking at these tables, we're looking at males. So let's highlight this really quick. So looking at males versus looking at widows. So notice how they overlap right here. Let's make that one a little bit darker. So they overlap in this one area right here. So because they do overlap in some way, there are people that are both male and widowed. So here where we looked at this one, probability of male, it was just equal to the number of males divided by the number of the sample space. Same thing with widowed, same thing with divorced, widowed or divorced. These two were disjoint, so we'll talk about that one too. Let's see if we could look at this. So, and there aren't any other N's, M, no other M's, widowed, W, divorced, and separated. Okay, so probability of widowed or divorced. So that was just the probability of widowed plus the probability of divorced. Now with this one, probability of male or widowed, this one is not disjoint. There are people that are both male and are widowed. So because of that, we have to use our general rule. So probability of male or widowed is equal to the probability of male plus the probability of widowed minus the probability of male and widowed. And now because of that, we have to get one more category. So here, so probability of male or widowed. Up here, we have to look at the probability of male and widowed. So that probability is going to come right over here, probability of male and widowed. So let's clear, or yeah, let's not clear it up. So probability of male and widowed, it's probability or the number of male and widoweds divided by the total sample space. So probability of male and widow is going to be this one divided by the entire sample space. And now that we have that, we could follow this equation to help us get this one down here. So probability of male or widowed is equal to the probability of male. So probability of male plus the probability of widowed plus widowed minus the probability of male and widowed. And there we go. So here we have that last probability, 0.5336. And that's it. So remember, we're looking at whenever we're adding these, the widowed or divorced, we're looking at event E or event F. If they don't have anything in common, then you could just add the two together. But if they do have something in common, if there are both males that are widowed or widows that are male, that would cause us to kind of count numbers twice. So we're counting these people in both male and we're counting them in widowed. So because we're counting them twice, we have to subtract at least one of them. Well, we have to subtract one of them. And let's see if we missed anything. So here, first add all the entries up. We did that. All right, so there are 1,260 or 126.9 million males 15 years or older and 260.1 million US residents 15 and older. So the probability that you randomly select a male ends up being this right here, 0.488. And that's what we got over here. Let's look at, I was being a little lazy. It looks like they only went out 3 decimal places. All right, so from here, part B, so the probability that you randomly select a 15-year-old and they're a widower, so probability of widow is this right here, 0.058, 0.058, perfect. The next one, the event of widowed and divorced are disjoint. So we use the addition rule for disjoint events. So here we just had to look at the probability of widow plus the probability of divorce. Add those together, cool. That's what we ended up getting, 0.167, 0.167. And now this one, so the events, male and widow, are not mutually exclusive. In fact, there are 3.3 million males who are widowed in the US. So therefore, we use a general addition rule to compute. So probability of male or widow. Here, it would have to be probability of male plus the probability of widowed minus the probability of male and widowed. And if we look at that chart, it ended up overflowing right here. So there's that. And lastly, compute the probability of an event using the complement rule. So complement of an event, let S denote the sample space of a probability experiment and let E denote the event. Complement of E denoted E to the power C. So complement of E is all outcomes in the sample space that are not in the outcomes of E. So if we were to draw a picture, we have our sample space. Wow, how pretty. So this is our event E. Complement of E is going to be everything not in here. So everything not in E, but inside the sample space. All right, so now the complement rule. If E represents any event, E complement represents the complement of E, then the probability of the complement of E is equal to 1 minus the probability of E. So kind of think of it. And one of those examples, let's just look at the numbers 1 through 5, 0, 1, 2, 3, 4, 5. So looking at those, let's make it a little bit cooler. So 3 and 4. So 1, 2, or 0, 1, 2, 3, and 4. So if probability of E is equal to 2 out of the 5, probability of E complement is equal to 1 minus the probability of E, which is equal to 1 minus the probability of 2 over 5, which if we were to add these or subtract these two, we would have to rationalize the denominator. So 5 over 5 is equivalent to 1 minus 2 over 5. 5 minus 2 is 3, so 3 over 5. Or you could have just plugged it into the calculator and seen that too. All right, so that's what it's going to look like. And yeah, so the entire region, the area of the region outside of the circle of E represents E complement. All right, so looking at this, according to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What is the probability that a randomly selected American has not played the state lottery? So what we're looking at is probability of playing, and that's 52%. And to turn this into a decimal, we would say 0.52. We would just divide our percentage by 100. So probability of playing is 0.52. And what they're looking for is select an American who has not played the lottery. So probability of not playing. So probability of not play is, notice how these two are complements of each other. They're the exact opposite. So there's not one person that could both play and not play. So you're either playing or you're not playing, or you have never played. So looking at these two, the probability of not play is going to be 1 minus the probability of play, which we already have that number. So 1 minus 0.52. 52, much better. And that would be equal to, we could plug it into a calculator, but if you're comfortable with doing that math in your head, that would be 4.8. So the probability of not playing would be 0.48. So probability not played state lottery is equal to 1 minus the probability of played state lottery and 0.48. Beautiful. All right, so the probability of randomly selecting an American who has not played a state lottery is 0.48. And looking at this data, so data in table 7 represents the income distribution of households in the US in 2017. So this is going to be a slightly more applicable question. All right, so let's take a snapshot of this. It's almost perfect. And we're going to use this to help us answer those last couple of questions. So insert data from table. And it should be this last one. Yep. All right, looks good to me. All right, so of this data, first question, compute the probability that a randomly selected household earned the following income. So 200,000 or more, 200,000 or more. Let's see. Just so we could keep it vertical, let's hit copy and paste. And that'll keep everything nice and pretty. Okay, so less than 10,000 is here, 10,000 to 14, 15 to 24, 25, 35, 35, 50, 50, 75. Okay, so it looks good. So what we're looking at is 200,000 or more. So again, let's look at total. So the total is going to be equal to the sum of this data set. Cool. So now we have our total and or our sample space. And now we're looking at probability of 200,000 or more. So equal to this value. So the number of 200,000 divided by the total. And that's how we got this value right here. And that answers this very first question. So total 7804, 7804. Oh, I see what they did. So they added all of them together and they got that 120, this one right here. So 7804 was the very first one. Okay, so they got the total number of people, the entire sample space. And from here, there were 8284, 8284 of 200,000 or more. And that's how they got the 0.069, 0.0, almost 69. There we go. So the probability of randomly selecting a household that earned 200,000 or more in 2017 is 0.069. If we randomly selected 1,000 houses in 2017, we would expect about 69 of them to have household incomes of 200,000 or more. All right, so now less than 200,000. So here we have our technology. We're able to add everything together, but let's see 2 different ways of completing this. So less than 200,000. So this one is 200,000. This one's 200,000. This one's 200,000. So all of these here are less than 200,000. So probability of 200,000 or more. Here would be less than 200,000. All right, so what we could do here is, so probability of less than 200,000. And this one could be, because we have to find the sum, so the number of less than 200,000. All right, so the number of less than 200,000 is going to be the sum of all of these here. So now the probability of less than 200,000 is going to be equal to this value here divided by the total. And we have that. Or another way we could see this is less than 200,000 is the complement of more than 200,000 or 200,000 and more. So the complement is going to be equal to 1 minus this right here, which ends up being the exact same thing. So the only reason I cut it off here was because we had it cut off. So 0.931, 0.931. Let's see if we increase this. Oh, it doesn't. Ah, that's why. I guess the same thing here. All right. I'll stop playing with it. But there we go. So complement was a lot easier to use than this one right over here. Having to find all of those. It's a really quick and easy way to find that solution instead of looking at all of them, adding all of those together, then from there finding the other complement and leaving it there. Ooh, okay, so at least, so find the probability of at least 10,000. So probability of at least 10,000. All right, so 200,000 or more is at least 10,000. 150 to almost 200, cool. All right, less than 2,000 or 10,000 is this one right here. So less than 10,000 here, then we could either add all of them together or just look at the complement. So this is going to be our at least rule. So here, let's input one more space just so we could find that probability. So probability of at least 10,000. Let's first look at the probability of less than 10,000. So probability of less than 10,000 is going to be equal to the number of less than 10,000 divided by the total. So here it's going to be equal to this number divided by this. And it's this. At least 10,000 is going to be this value plus this value plus this value plus this. So all of those at least is talking about the complement. So this is going to be equal to 1 minus this value here. So this is how we could get it using the complement. If you wanted to add them all up together, then you could, but it would kind of defeat the purpose of the complement rule, making it a lot easier to work with. So 0.935, let's see what they ended up getting. 0.935. So they did the same thing we did. So we looked at the probability of at least 10,000 and used the complement rule from finding the probability of less than 10,000. So the probability of randomly selecting a household that earns at least 10,000 in 2017 is 0.935. So if we randomly select 1,000 houses in 2017, we would expect about 935 of them to have household incomes of at least 10,000. And that's the end of the slideshow. If you guys have any questions, please email me. But if not, good luck. I'll talk to you guys later. Bye.